Hello friends, in this video we are going to discuss about the ambipolar transport. For this, we know that in a semiconductor, the whole current, that is the whole current density, can be given by a equation, that is Jp, and this Jp will consist two parts, that is Jp due to the drift motion plus Jp due to the diffusion motion. And these two motion phenomena, that is the drift and diffusion, will produce the total Hall current density, that is Jp. So we know the drift current density for the holes, that will be given by Q into mu p into small p into E, and the diffusion current density will be negative because it is a hole. So Q into dP into dP by dx, where the Q is the electronic charge, mu P is the mobility of the holes, and P is the concentration of the holes inside the semiconductor, and E is the applied electric field. Similarly, this dP in the diffusion current density equation is the diffusion coefficient for the holes, and dP by dx is the concentration gradient of the holes. Similarly, we can write the electron current density in this form, that is J suffix n, and this J suffix n can be written as Jn due to the drift plus Jn due to the diffusion. This can be written as Q into mu n into n into E minus Q into dn into dn by dx. So from this equation we can write that mu p and mu n are the mobility of holes and electron respectively. Similarly, P and N are the concentration of holes and electron respectively, and dP and dN are the diffusion coefficient of hole and electron respectively. Similarly, dP by dx and dN by dx are the concentration gradient for holes and electron respectively. So this is the current density equation of hole and electrons that will be needed for the ambipolar transport. Now, for describing the ambipolar transport, let us consider a semiconductor bar like this. So if we take a semiconductor bar, so this is a semiconductor bar like this, Now suppose in this semiconductor bar we have applied an applied electric field E applied externally, and after that we have given some excess carrier inside the semiconductor. So some excess carriers will be generated or created at some particular point. So let us assume that in the middle of the semiconductor some excess electron del n and some excess holes del p has been created at the middle of the semiconductor bar, where del n, that is del n, is the excess electron concentration and del P is the excess hole concentration. Now, since we have applied this E external to the semiconductor bar, so this excess electron and excess hole will feel some force due to this externally applied electric field. Since the del n, that is the excess electrons, are of negatively charged, that's why they will try to move in the opposite direction of the external applied electric field, and since del P are positively charged particle, that is holes, that's why del P will try to move in the direction of the externally applied electric field. Now, a situation will arise after the movement of the excess electron and excess holes like this. When they will be separated, that means the del n will be separated from the del P in this fashion due to the externally applied electric field, that is E applied. Now, when a separation between the electrons, excess carriers, and excess holes will be created in between the excess electron and excess holes, then at that point an internal electric field will be induced from the del P to del N. Let us denote this internal electric field by E internal. It will exist in between the two particles del N and del P, directed from del P to del N. This internal electric field will be produced due to the, so we can write E internal will be produced due to the attraction force attraction force between del P and del N. This attracting force will hold back the excess hole and electron back towards each other. So we can say that this E internal will hold back will hold back del P and del N together or towards each other. So right now we can say there is a total electric field on the semiconductor. So this E total can be written as E applied That is, if I do the mod, then mod of E total will be E applied mod plus mod of E internal. Due to this internal field, the negatively charged excess electron and positively charged excess holes will drift or diffuse together because they are bound by an internal electric field. They cannot be separated. So they will drift or diffuse together with a single effective mobility or diffusion coefficient. Hence, we can write that the E internal that has been produced due to the separation of del N and del P due to E applied. So E internal has been produced, and this due to this E internal, the negatively charged excess electron and positively charged excess holes will drift or diffuse together with a single effective mobility or diffusion coefficient. And this phenomenon of moving the excess holes and excess electrons together is called the ambipolar transport. In ambipolar transport phenomena, what is happening that the excess electrons that has been generated inside the semiconductor and the excess holes that will be generated inside the semiconductor, they will move they will move in the drift motion or diffusion motion together like a single particle, and they will have an effective mobility value. So this thing will move as a single particle, this whole thing, and they will have a effective mobility value if they move in the drift motion, and they will have effective diffusion coefficient value if they move in a diffusion phenomenon. Now, this effective mobility value, that is the effective mobility value, also termed as ambipolar mobility. And this ambipolar mobility, if we denote this ambipolar mobility by mu dash, then this mu dash will be depends on the mu n and mu p, and also the hole concentration and the electron concentration. So this mu dash can be written as follows, that is mu n into mu p into p minus n and divided by mu n into n plus mu p into p, where p is the total hole concentration, that is previously it was P0. After that, some excess hole concentration has been created, del P. Similarly, N can be written as N0 plus del N, that is del N is the excess electron concentration that has been generated after N0. and the ambipolar or the diffusion effective diffusion coefficient is also termed as ambipolar diffusion, and this ambipolar diffusion, if we denote it as d dash, then d dash will be written as dn, that is the diffusion coefficient of the excess electron, and dp, that is the diffusion coefficient of the excess holes, plus n plus p dn into n plus dp. Similarly, n and p will have this value. So mu dash and d dash are constant because electron and hole concentration Np will also contain the excess electron and hole concentration respectively. So we can write the mu dash and d dash as follows. So the ambipolar mobility value mu dash can be written as this form, like mu n into mu p into p. P means p0 plus del p minus of n0 plus del n mu n into n मतलब n0 plus del n plus mu p into p0 plus del p. So this is the value of the ambipolar mobility, and this is a very important term in the mobility of the ambipolar transport. If the ambipolar transport is happening due to the drift motion, then we have to use this effective value of the mobility. Similarly, we can also find, or also we can write the ambipolar diffusion coefficient d dash as dn, that is the diffusion coefficient of the excess electron, into the diffusion coefficient of the excess holes dp into n plus p. N value is n0 plus del n plus p0 plus del p, and dn into n0 plus del n plus dp into p0 plus del p. So this will be the effective diffusion coefficient value for ambipolar diffusion transport phenomenon. Now, if we consider a p-type semiconductor, then what will be the value of this mu dash and d dash for the p-type semiconductor? So let us consider a p-type semiconductor like this. So for p-type semiconductor, we know, if we consider low level injection in the p-type semiconductor, then we can write that the excess minority carrier concentration, that is del n, will be very much less than the majority carrier concentration, that was P0. Since but start since it is a p-type semiconductor, so we can say that the electron concentration inside the p-type semiconductor, that is the minority carrier concentration, must be very much less than the majority carrier concentration, that is the whole concentration, that is P0. So now we know that we have already found the ambipolar diffusion coefficient d dash, and the d dash value is given by dn dp into n0 plus del n plus p0 plus del p, and dn into n0 plus del n plus dp into p0 plus del p. Since we know that the excess electron concentration del n will be equals to excess hole concentration dp, so we can write that d dash will be equals to dn into dp n0 plus del n, and we have replaced this del p as p0 plus del n, because del n and del p are same. Similarly, it will be dn into n0 plus del n plus dp into p0 plus del n. Now we know that for low level injection, the del n value should be very much less than 0, and n0 value is very much less than p0 because it is a p-type semiconductor. So if we use this information in this d-dash equation, so the d-dash equation will be, you can see that this del n value, this del n value is very much less than p0, so we can neglect this del n value. Similarly, here we can neglect this del n value, and this n0 value will be very much less than the p0, so we can also neglect this total term n0 plus del n and n0 plus del n. So ultimately we can get a equation like this of d dash. D dash will be dn, this dn, then dp, so we can write dp. So we have neglected this term n0 plus del n, so there is only p0. So only p0. In the denominator, we will have the, we have neglected this n0 plus del n term, so this total term will be neglected. So we will have only dp, dp, and this p0. This, so this is the diffusion coefficient or ambipolar diffusion coefficient value for the p-type semiconductor. Similarly, we can also find that the effective mobility value for the ambipolar transport in a p-type semiconductor can be written as, using those consideration, this del n plus del p, and this consideration, if we use this in the mu dash equation, so it can be written as mu n into mu p into p minus n, that is mu n into n plus mu p into p. This was the equation. So if you use this approximation, then it will be nearly equals to mu n, and this d dashed value will be nearly equals to this dp, dp will cancel out, p0, p0 cancel out, so it will come as dn. So we can say that from this conclusion, from this calculation, we can see that for p-type semiconductor, Under low level injection, the ambipolar diffusion coefficient D dash will be nearly equals to the diffusion coefficient of the electrons, and the effective mobility value for the ambipolar transport will be equals to the mobility value of the electrons, and dn and mu n are constant, so we can say d dash and mu dash are also constant. This is the conclusion that we can draw for the p-type semiconductor ambipolar transport. Similarly, if we go for n-type semiconductor, then we know that under low level injection, low level injection consideration, we can say that the del p value, that is the excess hole concentration that has been generated, will be very much less than the electron concentration, that is the majority carrier concentration for the n-type semiconductor. And since it is a n-type semiconductor, so we can say that is the electron concentration n0 will be very much greater than the hole concentration P0. And if we use this consideration or approximation for the mu dash and d dash for ambipolar transport, we can see that d dash will be nearly equals to dp for n-type semiconductor, and mu dash will be nearly equals to mu p for p-type semiconductor. So, in an ambipolar transport, you can see that the ambipolar mobility is the minority carrier mobility, and the ambipolar diffusion coefficient is of the minority carrier diffusion coefficient. But here this mu dash value will be of minus sign for the n-type semiconductor. This is the difference. In the p-type it was d dash was dn and mu dash was mu n, but for the n-type semiconductor it will be dp and minus of mu p, and this minus comes from the following fact that the mu dash associated with the carrier drift, the sign of the drift term depends on the charge of the particle. The equivalent ambipolar particle is negatively charged, so you will get a minus sign. Now, if the ambipolar mobility reduces to that of the positively charged holes, then a negative sign must be introduced. That's why we have introduced a negative sign. So, in this way, we can discuss about the ambipolar transport in the semiconductor. And in the ambipolar transport, we have seen that for n-type and p-type or extrinsic semiconductor, the ambipolar transport diffusion coefficient and the mobility value depends on the diffusion coefficient value and the mobility value of the minority carriers. And for n-type semiconductor, for effective mobility, we'll have a minus sign extra here. So this is all about the ambipolar transport phenomena that will take place inside the intrinsic semiconductor, extrinsic semiconductors, that is n-type and p-type. Thank you.